Yeah.
Number 10.
Okay. Number 10.
I just kind of wanted to see what this was.
Homework. On stress tensors?
Yes. I'm not late, you're late.
Okay, so it's easiest with this kind of thing to just put it into the stress tensor and then fill in the missing stuff using symmetry of the stress tensor. But I guess I think it's probably valuable to be able to do it from the stress cube too, just to visualize what this symmetry means. The symmetry of the stress tensor means because there's this 1 megapascal thing going down, there has to be a 1 megapascal thing going this way. And because there's this 1.5 going forward, there has to be a 1.5 this way. And we only know about shear stresses shear stresses. So we can't say anything from that normal stress. And so this is it. Those are the only two shear stresses we had.
What about that?
Oh, you're right. I missed one. So that has to be this way. Okay, but the easier way to do it is just go to the stress tensor, fill in the values you have. Let's see, we got a x, y, so a 0xx, xy is -1, xz is -8. And then yz is positive 1.5. And then that's it. And now you can fill in the rest just using the symmetry. This has to be -1. This has to be -8. And this has to be 1.5.
ZZ is 6, right?
Dang it! Any questions about that?
You're late again.
How many times can you be late in one day?
I don't know, let's find out.
Okay, so any other homework questions you want to see? Okay, so we talked about how to calculate the normal strains. So let me do an example. So we're going back to definitions of strains. Definitions. Of the strains. So let's say that you start with a piece of material like this. Let's say this is 1 centimeter. And this is 0.008 meters. That is wildly out of proportion. And then after deformation, the long side elongates a little bit, the short side shortens a little bit, and we have 0.011 meters for the length, and for the height, we have 0.007 meters. And the Z is unchanged. Bless you. We're using a coordinate system like this.
Is it
Yeah.
like a 10% change, way too high?
Yeah, so that's one of the, and that's exactly how I want you to think of it. Yes, it's way too high. So, so what we're going to do here is calculate the normal strains. And then we're going to ask ourselves, is this a realistic deformation? But Justin already ruined this part. He ruined the whole punchline of this problem.
It's good for us to get used to disappointment.
Yeah. So is it a realistic deformation for this class? And what that means is an elastic deformation with a linear, let me put these in the other order. So for a linear elastic deformation of an engineering material. That's kind of like a mouthful, but that's sort of what this is getting at. So what does linear elastic mean? Elastic means if you remove the loads, it'll go back to its original shape. Okay, so once you get to permanent deformations, it's not elastic anymore. Linear means this linear relationship between stress and strain that I mentioned last time, that this whole class, all of our calculation techniques are based on. And then engineering materials, so we're talking about metals or concrete.
Does wood fall under that?
Wood is, yeah, also has a good linear elastic region. Bone has a good linear elastic region, so you can do this with biomechanics stuff. Okay. So the way we're going to do this is the X normal is the final length minus the starting length in the X direction divided by the starting length. And so that's 0.001 divided by 0.01, which is 0.1. And you can see why this is unitless. I mean, you're just dividing length by length. And now let's look at the Y normal strain. So that is the final length, 0.007 minus 0.008 divided by 0.008. And you get negative 0.125. And then in Z, I said that the length is unchanged, so you would expect that to be a zero deformation, and that's what it is. It's like whatever the starting length in the Z direction is the same as, or whatever the ending length is the same as the starting length divided by L sub 0, and so that gives you 0.
So do we always use like it's not like L sub 0 Y and L sub 0 X.
I mean, I guess, yeah, you should probably do that. I think I left it off just because it starts looking kind of messy, but, and these are way too big to be realistic. If you did this to metal, it would be drastically permanently deformed. It might be able to stretch that far before it snaps, but and one other thing to notice is in what dimension is it stretching and what dimension is it contracting. The positive means that it's stretching in the x direction. The negative means that it's contracting in the y direction. Okay, so positive 0xx means stretching along x. And the negative EYY means contracting along y. The 0 EZZ, that just means that it's unchanged along z. Okay, so now we have to define the shear strains. Do you remember what kind of deformations shear strains represent? Those represent angle changes, so the thing being like tipping over and stuff like that. Let's call this angle changes between the faces. Okay, so this is the notation I'm going to use. Theta AB, let's call that the angle in radians. Between the positive A and the positive B faces. And this has to be after the deformation. We're going to name the we're going to name these shear stresses. This is gamma, right? Gamma. So gamma xy is pi over 2, which is the original angle between the positive x and positive y faces, minus the final angle between the positive x and positive y. Gamma xz is pi over 2 minus the final angle between the positive x and z faces. And gamma yz is pi over 2 minus theta yz. And one thing to notice here is, so think about what these signs mean. Positive shear strains mean the angle between positive faces gets more acute. And a negative shear strain means the angle between positive faces gets more obtuse. Okay, these are important. I'll put a box around them. And notice that, so the normal strains were unitless because we took a length and divided by a length. These are also unitless because radians are not really a unit. So let me do an example. So let's say that we start with a shape like this. It doesn't matter what the lengths are for this one, where these are all right angles. And let's say we are looking, I'm just jumping right into it here. Let's say this is the direction of the x-axis, this is the direction of the z-axis, which means the y-axis is going into the page. And after the deformation, let's say that this thing looks like this. Where this angle is 1.43 radians. And that's all we need to know about it because it's a parallelogram. And the other angles that we can't see are unchanged. Well, yeah. And we want to know what are the shear strains. And then we want to know, are these realistic in this class? For linear elastic, range, okay. All right, well, we're looking at this in a funny way. The first thing we have to do is identify what the positive, so notice that this is gonna affect the XZ normal strains, right, normal strain. But the number that's given, like first we have to identify what the positive faces are. So on this parallelogram after the deformation, or let's do it first on the regular one next to the coordinate system, the positive Z face is this thing. Okay? The positive face is the one where if you put the origin inside the element, it's the face that the axis is coming out of, like alien. Okay? So this is positive Z. This is positive X. So this is positive X. This is positive Z. And so in other words, the angle that we want to calculate the shear stress is not this 1.43. Okay, but we can figure out what this is because it's a parallelogram. So this just has to be pi minus 1.43. So that's equal to 1.71 about. And so shear xz, gamma xz, is equal to pi over 2 minus 1.71, and that's negative 0.28. It makes sense that that's negative because that angle is getting more obtuse. And is that realistic? No, nowhere near realistic. Okay, any questions about that? So whenever you're thinking of strains, at least until it sort of happens in your head naturally, think about those meanings, okay? When you see the shear strains, think about those angle changes. When you see normal strains, think about stretching and contracting. So how are we going to format the strain? With stresses, we had two ways to do it. We had the stress tensor and the Voigt stress. There's no strain tensor with the way that we've defined strains. You can define a strain tensor that meets the definitions of a tensor, but we're not using it in this class. So for us, there's only the Voigt strain. And it goes in exactly the same order as the Voigt stress. So this is the normal strains in order. So we have EXX, EYY, EZZ, and then we have the shear strains in the most nonsensical order you can imagine. Gamma YZ, gamma XZ, gamma XY. Okay, and so now I've been saying that in this class, we always have this linear relationship between stresses and strains. So let's talk about what that relationship is. It's called the constitutive relationship. So it's like, how is this thing constituted, you know? This is a Hookean material. Which is also the same thing as saying it's linear elastic. And the relationship that we're going to use is that the Voigt strain is equal to a matrix times the Voigt stress. This matrix C is a 6x6 matrix called the compliance matrix. This is the form we're going to use the most often because the techniques we're going to have will allow us to calculate the stresses and then from that go to the strains. It's not going to allow us usually to calculate the strains and then go to the stresses. But there is also, so I'm going to put this in parentheses because we won't use this as much, but this is equivalent to the relationship that says the Voigt stress is equal to a 6x6 matrix called the stiffness matrix times the Voigt strain. And the relationship between these is C is the inverse of E, and therefore E is the inverse of C. And your calculators will do those inverses for you. So if you can calculate one, your calculator will do the rest. And just to sort of get you used to, I have this in here, so let me get this in your notes. So this compliance matrix, if somebody throws a chunk of engineering material, let's think of steel as our kind of go-to engineering material. Someone whacks you in the head, chucks a chunk of steel at your head. Would you be more likely to think, wow, that was compliant? Or wow, that was stiff? Stiff. And so the stiffness matrix has big values, and the compliance matrix has tiny values. Okay, like someone chucks this thing at your head and says, was that pretty compliant? And you'd say, no, not at all, a very small amount compliant. And so that's what those tiny values represent. Okay, so these are going to be like 10 to the minus 11 and stuff like that. Okay, really, really tiny values. And these will be 10 to the 10 and stuff like that. Okay, so let's start thinking about this compliance matrix. So what's the worst case scenario? So what we have here is we know that we have this linear relationship, and we know once we fill in this matrix, if we know the stress, we can calculate the strain, and that would be a really powerful thing to be able to do. But in the worst case scenario, we would have to fill in 36 separate values, and each one of those values would come from a separate type of measurement, which would just be a nightmare to deal with. Like, so at worst, this compliance matrix could have 36 independent values. But we're super lucky. The materials that we're dealing with are what's called isotropic. And isotropic means that they have the same behavior, the same flexibility, strength in every direction. And for isotropic materials, So I want you to soak in how amazing this is. For isotropic materials, those 36 values are all determined by just two independent parameters. Those parameters are called capital E, like the stiffness matrix, but this isn't a matrix, it's just a value. And nu, the Greek letter nu, and these are measured from one simple tensile test, measured by a simple tensile test where all you do is you stretch this thing, you measure the force, you measure the deformations, and that's it. So it's incredible that this is possible, that we can get so much power out of these very basic measurements, but we can.
Is it just like a hydraulic thing that you just like?
Yeah, so I guess I don't know how they do it, but man, you sure would think it would.
I think there's one in the lab
You-
room that we do. Like it's just like a
Yes,
it's just like a thing, and it's got like a hydraulic ram, but it looks like it pulls. Apart.
yes. And it pulls, yeah, you put like a piece of steel or whatever in there, and it has to be so precise because we're talking about such small deformations. And I will tell you, if you've seen that machine, when I was in graduate school, I was the TA for a class where we did tensile testing, and something was wrong with the settings, and so it, instead of just going for a while and then stopping, it went all the way until it popped. And when you pop a steel sample, man, it's a very scary noise. It's a very alarming moment when you're just going about your normal day. So, okay, this test is called a tensile test, and I'll talk more about that pretty soon. Okay, so let's talk about what these two values are. And then by the end of today, I'll give you the form of this matrix. It's already in your notes from a while ago, but okay, so E. People call it three different things. One is Young's modulus. Or sometimes you hear modulus of elasticity. Or the stiffness. For metals, the range is around, let's say, 50 to 250 gigapascals. 100, no, I have that wrong. Megapascals. 150. Now I'm second guessing myself. Let me think. A gigapascal is, yeah, it is gigapascals. So a bigger value is a stiffer thing. You know, steel has a very big Young's modulus. Gold has a very low Young's modulus for a metal. And then this one is called Poisson's ratio. And for metals, it's usually right around 0.3. And so if you ever see a problem or you're ever doing something involving metals and you don't know what the Poisson's ratio is, 0.3 is a perfectly good thing to put in there and guess as a guess, you know. And so the Young's modulus tells you the stiffness. The bigger it is, the less the thing stretches for a given amount of load. Poisson's ratio tells you so when you stretch something and it's a solid, you have a solid block of something and you stretch it, the sides are going to tend to contract in, okay? You can think of that, the effect is kind of preserving the volume, although it usually doesn't totally preserve the volume. So if you stretch out, the sides go in. If you compress down, the sides go out. If the material, let's put this here. If a material is incompressible, that means that the volume is constant. Then Poisson's ratio is equal to 0.5. A Poisson's ratio of 0 means that there's no effect. You stretch it, you compress it, there's no effect on the perpendicular directions. One material that has almost exactly 0 Poisson's ratio is cork. And it makes sense that cork, that property makes it useful for plugging glass bottles, because if you have to whack a piece of cork with a hammer to get it into a glass bottle, you don't want it to expand in the other direction when you do that and crack the glass. So that's sort of what makes it useful as a wine stopper.
Why is it like 0.5 and not 1?
Well, yeah, when I give you the mathematical definition, we can show that. It's because, I mean, it's defined by a mathematical formula and not by like what sort of would make sense, you know. The range of possible things is 0 to 1. No, is that 0 to 0.5? It can't go to 1. Okay, so if something was bigger than 0.5, it would mean that you would compress it a certain amount and it would like get so angry that its volume increased by going extra. That would be like the Hulk version of the Poisson's ratio, but that materials don't do that. So the biggest Poisson's ratio you can have is for something that's incompressible. Okay, so here's how the tensile test works. How much time do we have? Okay, so you take a sample that's shaped like this, sort of thinner in 2 dimensions, longer in the dimension that you're going to stretch. And you put it into a system between 2 clamps. I don't really have a good type of clamp in mind, but that's what this is supposed to indicate. and you stretch. And we're always going to use a coordinate system where the x-axis is lined up along the loading axis. The y-axis is like this, and the z-axis is perpendicular. So there's x, y, and z. And as you stretch this, so you apply this tensile force F. You measure the deformations along X, and either Y or Z. Either one of those is fine. Once you do that measurement, to calculate E, your sigma XX is the force divided by the cross-sectional area. So this is the tensile force. This is the cross-sectional area. Your XX normal stress is the deformed length minus the original length divided by the original length. And E is that XX normal stress divided by the XX normal strain. And since this is units of pascals divided by something unitless, this has units of pascals, megapascals, gigapascals. And then to calculate Poisson's ratio, I'm going to do it with Y, but you could also do it with Z. We're also going to measure the Y strain, normal strain. And this is the final length in the Y direction minus L sub 0 divided by L sub 0. And Poisson's ratio is the negative Y strain over the X normal strain. And you would get the same exact thing if you did the measurements with Z. So it's also equal to negative EZZ over EXX. And since you're calculating this by dividing two unitless things, this is also unitless. Okay. Now once you've calculated these, the compliance matrix has this form. So you've written this down once before. I think it's sort of helpful to sort of get it in your head. So let's just do it again here. So we have this pattern that you follow, and you have to sort of recognize the pattern. You don't want to just try to remember everything in here. So the 1, 1 element is 1 over E. And then the next two elements in that row are negative nu over E and negative nu over E. And then you have 3 zeros. And the first 3 rows of the compliance matrix just keep having the 1 over E move to the right in that pattern. So the next row is negative nu over E, 1 over E, negative nu over E, and then 3 zeros. And then the last one with this pattern is negative nu over E, negative nu over E, 1 over E, and then 3 zeros. And now we're on to the second pattern, and that is all the first 3 elements are 0. Then we have this kind of ugly thing that's 2 times the quantity 1 plus nu, all divided by E, and then zeros. And the pattern for these last 3 rows is just that ugly thing keeps moving 1 element to the right. So the next one is 0, 0, 0, 0, 2 times 1 plus nu over E, 0. And then 0, 0, 0, 0, 0, 2 times 1 plus nu divided by E. Okay, so with this matrix, if you know the Young's modulus and the Poisson's ratio, then anytime you know the stress, you can calculate the strain at a given point. And also, anytime you have the strain, you can calculate the stress. That's just less common for us. Okay. And so since this is the constitutive relationship that we're going to use, I want to write down the 4 big assumptions that we're always going to make in this class that allow us to use this. So let's call this the 4 big assumptions that allow use of the compliance matrix or the stiffness matrix. The first one is small deformations. This never works if you have big deformations. And to us, small deformations means strain values less than around 1 times 10 to the minus 4. The second one is linear elasticity. Or in other words, Hookean materials. So this never really works for rubber, is the example that is the most obvious example. It doesn't work for polymers very well, but it works for steel and concrete within a certain range. The third one is the materials have to be homogeneous. So that means wherever you go in the material, the material is the same. You can't have pockets of one kind of metal embedded in another kind of metal, okay? Think of like homogenized milk, like they blend it to distribute all the blood and hair and fat and rat feces evenly. And the last one is isotropic. And that means same material properties in every direction. And these four things, they won't come up in just one quiz. They'll probably come up in 3 quizzes during this semester because it's really important that you remember this, okay? So just take a little time and memorize those and make sure you understand what each one means, okay? All right, that's it for today.